For decades in high-performance product design, the way things looked was mostly an accident. The aesthetic was rarely chosen. It was simply whatever form managed to survive the gauntlet of engineering requirements. Take carbon fiber. Nobody originally picked the black twill because it looked appealing. It was the material that worked structurally, and that dark, stealth aircraft aesthetic arrived right alongside it. It was an engineering default, handed down the line. Even early sustainability efforts fell into this trap. Recycled plastics and discarded fabrics were typically shredded into anonymous composite boards, which designers then had to hide deep inside the product's interior. When it came to putting those parts together, the solution was almost always a bath of industrial chemical adhesive. It created a seamless exterior, but it permanently and irreversibly fused those dissimilar materials together, erasing the junctions completely. Now, a completely new set of structural materials has arrived on the market, and they are breaking that monopoly. The old engineering defaults are no longer the only viable options. The moment you have a real working alternative, a material stops being just an unchangeable law of physics. It turns back into a conscious design choice, and that means somebody, somewhere, actually has to argue for it. Walk into a modern design studio today, and you will see teams moving away from passive acceptance of those old standards. Instead, they are making active, deliberate choices about the outer shell, often prioritizing raw, confrontational textures. The most obvious example is the move away from carbon fiber. Companies like B-Comp and BMW are pushing flax composites as a structural alternative. They hit engineering metrics, but read completely differently. Under a clear resin, flax exposes a warm, golden tan diagonal weave. It feels organic in the hand, placing the final aesthetic much closer to crafted timber than to a cold piece of aerospace hardware. Carbon black is suddenly no longer a given. This exact shift is happening beneath the outer shell. We are seeing a new methodology for handling discarded synthetic garments and factory offcuts. Instead of shredding waste into mush, designers take textile offcuts, compress them into mild steel cages, and heat treat them into structural blocks. The crucial move is leaving the cage in place as visible formwork. The waste stays readable as compressed, layered fabric. Whether it's the golden weave of a flax exterior or the exposed strata of recycled interiors, the structural material isn't being hidden away. It's being brought forward and used as the primary, visible surface of the product. If we look closely at how these new surfaces actually meet, we have to examine the literal connections holding the product together. Bonded assemblies make interior trim unrecyclable. Applying chemical adhesive permanently fuses dissimilar materials, so you can't get them apart. This modular sneaker concept rejects glue, joining a 3D printed sole to a leather upper by wrapping a rope fastening around the pieces. Because there's no adhesive, the owner can completely separate the sole from the upper by hand. You don't need heat guns, no chemical solvents, or even a basic tool. Creating a cabin or a shoe where every junction is a visible mechanical joint is a functional design language that achieves genuine physical sustainability in the real world. Zooming out to the entire life cycle of a product, there is a very specific window where these material and assembly choices have to happen. What a part is made of, and exactly how it is joined to the part beside it, are the foundational variables. Those two choices quietly set the boundaries for everything the visible design is allowed to become later. Because we are no longer relying on standard engineering defaults, that aesthetic destiny has to be forged early. It happens exclusively in the concept phase. A recent Depix design study illustrates this perfectly. They designed a performance shooting brake to test how a warm, natural fiber composite on the aero parts would read against a cold exterior body. They generated the entire study as a picture, rather than a written paragraph. They needed to test the visual argument and prove the structural logic long before any physical prototypes were built. Pivoting to a new material or a mechanical joint is flexible and cheap while you're still drafting, but once the factory tooling begins, those decisions become economically brutal to change. You have to see every angle and understand every material long before you start to build.